Let's start my presentation on an APT-Style Cyberattack testbed for the year. This research was conducted with Bohyun An, Jin-sang Kim, Dong-jun Won, Young-tae No, Jin-chun Choi, and Tae-shi Kim. First, let me introduce myself. I'm Kyu-chan Park, a master's student in the Power System Lab at Inha University of Korea, under the guidance of Professor Dong-jun Won. My main research fields are multi-microgrid, DC microgrid, energy storage system, and cyber physical system. I have worked on 5 projects so far, and I also wrote 5 conference papers and participated in 2 patent registrations. This paper proposed an APT-Style Cyberattack tested for the year in cyber-physical environments. The proposed security testbed consists of a real-time DR simulator, a real-time cyber system using real network systems and a server, and penetration testing tools generating APT-style attacks as cyber events. Moreover, this paper provides a cyber kill chain model for a DR system based on a latest MITRE cyber kill chain model to model possible attack stages. Currently, penetration of distributed energy resources such as renewable energy systems, energy storage systems, electric vehicles, and controllable loads in electric power systems are rapidly growing, and operation of the DR has been more and more important for secure and resilient power grids. However, cybersecurity vulnerabilities and challenges arise due to extensive information exchanges between DR and multi-party, such as utility aggregator control system and vendors using interoperability standards with high-speed networks for real-time monitoring and controlling the DR. APT can gain unauthorized access to a DR party server or network and remains undetected for an extended period to possesses extensive knowledge of the systems. Thus, immediate action to prevent, detect, and mitigate the APT attacks is required. This paper proposed a real-time hardware-in-the-loop cybersecurity testbed for DER. The proposed testbed enables to generate APT-style attacks and observe impact on DER and a local grid. As a result, researchers can analyze the complex interactions in a cyber-physical environment, specifically stealthy attack processes by APT. Furthermore, a cyber kill chain model that representing attack stages of APT for a DR system is designed based on a latest models ATTCK for industry control system. Figure 2 shows an overview of the real-time Hill testbed, including a DR physical system simulator using a real-time grid simulator, a cyber system testbed using real network systems and a server, and penetration testing tools generating live APT-style attacks as real cyber events. I explained DR system modeling and grid simulation. Figure 3 illustrates an example of a DR system in IEEE 13-node test feeder circuit, where the DER system consists of multiple smart inverters, a swing bus, a wind turbine, a PV, an energy storage system, and loads. The system bus frequency is 60 Hz and the nominal voltage is 4.16 kV. Smart inverters of wind turbine and PV perform maximum power point tracking control. The wind turbine is applied with the PMSG motor and the rated power is 2.2 megavoltage ampere. The PV is located on bus 675 and the rated output is 1 megawatt. The ESS capacity is 1 megawatt hour and lithium-ion battery model is used. Except for the bus where the generators are connected, the resistive, inductive, and capacitive loads are evenly connected to the other buses, where the real power demand of the distribution system is 3.5 megawatt. The reactive power demand of inductive loads is 2.102 megavar, and the reactive power demand of capacitive loads is 0.7 megavar. The impedance values between the buses are chosen based on the IEEE 13 bus system. The DER aggregator is installed in a cloud computing server, monitors the DER system data and sends control commands to the DERs. An operative power grid simulator simulates the DER system in real time. In this paper, because the target of the cyber attack is the ESS reference, I explain in more detail. The DQ0 current reference is expressed as equation 1 and 2. Equation 5 and 6 represent drop control as the primary control, and equation 3 and 4 indicate the active power and reactive power reference of the battery. For the control, the inner control loop is used and the related formulas are as equation 7 and 8. A battery is simply modeled as a voltage source. So, this figure is an implementation in MATLAB Simulink of what was described in the previous slides. The next chapter is cyber system simulation. A cyber system simulation for the DER system is designed by real network devices and a cloud server. Network layers of DER inverters are emulated by using Raspberry Pi, including Modbus TCP. The cloud server can emulate multi-party activities such as a third-party DER aggregator manages a group of the DER and communicates with utility DER management system. DER vendor assesses DER devices for software update or maintenance. And DER operator and owner can assess DER. DER smart inverters send system data to the cloud server, while the cloud server sends control commands to the DER. Field network devices such as a gateway and switches are installed with a firmware. So, Figure 5 shows the proposed APT-Style Cyberattack testbed. Figure 5 describes an example of the APT-Style attack model targeting to disrupt DER smart inverters, which includes a 12-page cyber kill chain model designed based on ATT and CK for ICS framework and several real attack incident reports. The Cyber kill chain scenario for the DR system is explained in this slide. First, initial access. Malicious APT actors infiltrate the first target DR aggregator server by leveraging initial access activities such as a software supply chain compromise and a password leakage attack of VPN enabling remotely access to the main control system. Second, execution. The adversary remotely modify a source code of the firmware inserting backdoor malware. This backdoor malware involves unauthorized third-party open source tools URLs and inappropriate code signings integrity checks. Third, persistence. Through the backdoor, the attackers masquerade as authorized users after accessing their target networks. Fourth, evasion. Due to the weakness in code signings and incorrect code integrity checks, the backdoor malware passes the IDS. Fifth is discovery. By exploring the DR aggregate server or connected external devices are synchronized. Sixth, lateral movement. The threat actors infiltrate the network layer of smart inverters through the gateway. Seventh is collection. All valid IP addresses of smart inverters registered in the DR aggregator server are collected. Eighth, command and control. Man-in-the-middle attack in the DR OT network, which has less visibility, is commanded to control the final target DR system. Ninth, inhibit response function. A real-time vigilant monitoring program is disarmed by a combination of malicious tools and man-in-the-middle attacks, such as DDoS attacks. Next, impair process control. Even though authorized asset owners and operators from the utility command a valid signal to control the DR system, the signal is sniffed then maliciously modified in the middle. 11th, impact. Due to the compromised cyber systems from the DR aggregator server to smart inverters, the physical layer of the DR system is crippled by nefariously manipulated controls. The last one is concealment. After achieving their goal, all forensic evidence is destroyed by wiping hard drive data by executing the pre-installed malware. Penetration testing, also referred to as red team activities, reproduce widespread cyber attack techniques manipulating the target DR system by using penetration testing tools. This paper only focuses on the operational technology side penetration testing events. That is, page 6 to 11 of the previous slide. Kali Linux, a publicly well-known advanced penetration testing and digital forensic open source platform, provides several hundred cyber attack tools to emulate more realistic APT attacks. The penetration testing environment has been established with a local area network connection between the operating system and a Kali Linux OS PC. Metasploit tool has been used to create the backdoor malware injection event, After then, for man-in-the-middle attack, error capture has been applied to mimic the set point change and control manipulations. From now on, each validation. DLL injection on Metasploit with escalated privileges enables a threat actor visits a target system via executing a malware. In this paper, it is assumed that a backdoor injection task with high privileges has already achieved through phase 1 to 5. Therefore, a man-in-the-middle attack with error cap assessing the system remotely is validated. So, for the simulation, by the presetting of man-in-the-middle attack code shown in Figure 7, a control command of an inverter is manipulated at 10, impacting a reactive power output. Figure 8 shows the reactive power output of the ESS. At 10 a.m., even though an operator had changed a set point of ESS reactive power output as 0 var, the man-in-the-middle attack code successfully intercepted the command changing as 500 kV. Figure 9a and b can compare impacts of DR and the grid. In the normal operation of the distribution system after 10, the peak current is 400 ampere as shown in Figure 9a. The reason why the current value fluctuates at 10 is because the active power reference of the ESS has changed according to the original scheduling. Compare with graph A, the peak current becomes 700 ampere due to the man-in-the-middle attack case as shown in Figure 9b. The straight line that appears a little after 10 occurs because it is a real-time simulation. It is noted that the output current of the ESS increased by 300 ampere by the man-in-the-middle attack, which may cause equipment failure, stability problems, and economic loss of the system. Therefore, it is verified that the man-in-the-middle attack caused the smart inverter, consequently negative impact of the local grid stability. This paper proposes a real-time co-simulation cybersecurity testbed for DR systems. The proposed testbed provides a comprehensive ICS or SCADA modeling and simulation hardware in the loop capability by capturing the cyber physical impact of DR control system operations and emulating targeted cyber events by APT attackers. Therefore, security defenders can use the proposed security testbed to prevent, detect, and mitigate the sophisticated attacks by APT groups. Future testbed works includes simulating more penetration testing events and covering or cyber kill chain pages. Thank you for listening to my presentation.